A very disappointing note I want to make of establishment astronomy and geology is they both stick the Earth in its grand nature into just being a bunch of gravitationally clumped rocks. See, don't ask how the rocks got there. Don't ask why everything's all different. Don't ask why Jupiter's atmosphere looks all like a giant blender. Don't ask why they radiate heat. Don't ask any of that. Don't ask why Earth has an iron core. Just explain it all away as being gravitationally clumped rocks. Now, my question is, do you believe the Earth was formed just from gravity alone and just came to be as is with the complexity of the surface features that we see? I don't think so. What they're doing is brushing every single other science under the rug. They're throwing it under the bus. Say, to hell with your sciences. It's all gravity. Einstein was a genius. Don't ask me any more questions. That's their attitude. But here, I will show you it's much more than that. You have intermolecular forces involving lubricants, oils, the hydraulic properties of supercritical fluids, etc., inside the interiors of gas giants, inside of red dwarfs as they evolve and form their cores. Number 2, concentration of fluids with respect to gas pressures, liquid pressures, etc. So you could have a concentration of helium gas inside of a certain area next to another concentration of, say, supercritical silicon, which would be really strange. What would happen if you change the pressure, the gas pressure, or the liquid pressure of those two materials and they interact with each other? Very, very strange phenomenon that we can open our minds to and be creative about. As long as you look at the Earth itself and try to reverse engineer the Earth into forming those types of materials, or figuring out how those materials could have come to be, in other words. Number 3, soaps and surfactants, acids, bases, redox reactions. This is where I think the essence of life formation is, right here. I think that's the bread and butter of life formation. But gravitationally clumped rocks, they don't want to worry about soaps and surfactants, meaning they don't care about how life forms. So it should be obvious what they do. They say a comet just seeds its life everywhere. Comets grow life and it comes from somewhere else. It's really strange, to be honest. And then you have solid state and surface chemistry. Say you have a cube of a material. What happens purely on the surface? And if it has holes, then you can go inside and then you can do calculations per its volume. But really, if you increase the volume per surface area, you can have a better catalyst, such as platinum. They use platinum as it's an excellent catalyst. It does a lot when it changes chemicals around. As well, there are other types of catalysts that exist, such as catalysts being enzymes when life forms. So you can have catalysts up here as well, making different types of chemicals, decomposing different types of chemicals. You could write spend your entire life just on that stuff alone right there. Number 5, natural internal refrigeration, as well as exothermic and endothermic reactions inside the star. So there are cooler and hotter spots inside of the star based off of what chemical reactions are taking place. That would be very, very interesting to look at. Number 6, chemical and physical changes, as well as thermodynamic phase transitions, plasma to gas to liquid and solid material. You have chemical reactions being ignored by geologists and astronomers. So when you study chemical reactions and apply them to stellar evolution, you're going to be way beyond them. They're just going to look at you as if they're going to have the deer in the headlights look, in other words. And physical changes, including the rock cycle and basic stuff like that. Number 7, the role of diminishing gravitation during evolution. And you need to calculate the rate of mass loss due to CME, solar wind, etc., and the rate of mass loss due to being adopted by a hotter host star, which would photoevaporate the outer layers and cause different kinds of chemical reactions to take place, meaning the star can eject new types of material inside of it, which will rain down inside of it. But that's an interaction, so it's not based solely on the star itself, but another one. So this can involve other stars as well. Well, as well as all those, because obviously if you heat the gas up, it increases its volume. So you should learn that when a gas giant gets closer to a host star, it puffs out. Meaning if we find a puffy gas giant, it was probably recently orbiting another hotter host star, but more on that later. 8. Phase transitions for pure materials and mixtures. This is big time. Different types of mixtures are in different phases per temperature, per how pressurized they are. You can spend your whole life just studying that stuff right there. The colligative properties of solutions. This has to do with how well they stick together and how well they can be broken apart. This has to do with crystal formation. How does amethyst form? How does quartz? Quartz is amethyst. How does that form? How do diamonds form? How does all that stick together? How is it that they form these perfect crystals and in the arrangements that they are, and that they can manage to clump together in the amounts that they clump together in? 10. No, wait, what is this? That was 9. 10. Stages of chemical equilibrium during early, middle, and late stages of evolution. So you have a sort of quasi-equilibrium per stage of evolution. So, meaning if you look at a sun-like star, it's not going to be exactly like a red dwarf in its chemical composition, because a lot of it's radiated away, a lot of it's recombined into gas, and all of that gas has combined back into different kinds of molecules. And the star is cooled considerably, so less and less stable molecules can be held together because there's not that much heat to break them apart. So you can include all that, including gas giants, and even late stages. Rocks are in chemical equilibrium. That's why they're so stable. That kind of stuff. 11. Chemical kinetics. The kinetics of chemistry, or the chemical motion, basically. How fast certain molecules can move. I know I talked to my father about fluid motion inside of tubes when you do calculations concerning viscosity. And there was another, I think, Reynolds number. He told me something about the Reynolds number being 2400. There was a certain cutoff point, but I'll have to research more into that. Then you have 12, photochemistry and electrochemistry. Now, I added these in the last, but these are very, very, very big. Don't let the last designation fool you. The amount of photochemical reactions that take place inside of a star are incredible. And this has to do with multiple stars. So you can have a hotter star releasing heat, energy, and light to an older star, and that older star undergoing photochemistry and forming a whole bunch of different kinds of elements. And I remember when I first started developing this theory, I immediately realized that maybe the process of photosynthesis starts high in the atmosphere of the late stage blue dwarfs, such as Neptune and Uranus, and then rains down on the interior. So whatever chemicals are needed to spur the act of photosynthesis, that happens in the high atmosphere due to another host star heating it up from the outside and then raining down. But I also stated, well, that's why Uranus' atmosphere is green, because that's the photochemical reaction taking place to allow for the process of photosynthesis to start occurring. But that was quite a leap, actually. And then you have 13. You have magnetic properties of material, very important. And you have 14, the electrical properties of material. This includes electrically conducting material and electrically insulating material, which are both very valuable. You need both insulators, which means no electric current at all, or magnetic field, and you have electrically conducting material, which can produce a magnetic field. So you have a dichotomy there. All right, I think that really sums up some basics people should look at if they want to explain star evolution or planet formation, which is exactly the same thing. So I might add, Is the Earth just a bunch of gravitationally clumped rocks? No, it isn't.